I would like to thank everyone for attending this presentation. As mentioned just a few moments ago, my name is Nathan Benetten. I am a senior bridge engineer at WGI, and I am a licensed professional engineer in California and Florida. I currently work here in our WGI Tampa office. Over the course of my career, I have used multiple analysis software programs for various bridge projects, ranging from flat slab cast in place concrete bridges, steel plate girders, steel twin box flyovers, and post-tension segmental bridges. Today, I hope to highlight some of the strengths of MIDAS Civil as an analysis tool. And while going through similar presentations online, I've noticed that a lot of emphasis and what YouTube video clicks seem to be from younger students and young engineers that like to use this information as a learning tool. So I will try to go through and explain all of my inputs clearly. I apologize to any senior engineers listening who would like to discuss complex topics and analysis. I will touch upon that, but I'm going to try to skew this a little bit towards the introductory side, but hopefully everyone can get a good feel of what MIDAS is capable of. So with all that said, let's begin our investigation for this two-span steel plate girder structure shown in this slide currently. And you'll see here just a couple of quick renderings that the people at MIDAS were great to make for us. You see here it's just a simple symmetrical two-span structure supported by a steel straddle bent. Now, over the course of this presentation, I'm going to address the following topics. First, I'm going to briefly go over the MIDAS Wizard's input settings to show how simple it is to even model some more complex steel structures. Also, too, there are a lot of times when bridge projects require special geometry that cannot be fully encapsulated in the MIDAS Wizard input. So what we're going to do here is we will include the use of a straddle to show how similar geometry adjustments can be quickly done outside of the wizard file. And then I will briefly go over how to apply a live load in MIDAS Civil, and then also go ahead and visually inspect some of the vehicle pattern shows just to make sure that we all agree visually that the live loads are being applied correctly. Next, I will just use MIDAS Civil to provide the ability to use their construction stage analysis. I plan to highlight how to perform the analysis in MIDAS Civil and why it's important to consider the effects of construction staging for steel structures. And also, this is becoming more and more important for many DOTs across the country. And then finally, I will compare the results from MIDAS Civil, analysis results with MIDAS Civil with MDX to validate the presented analysis results. Hopefully, through the course of this presentation, I hope that everyone kind of takes away the following items. One, I hope that MIDAS has the ability to provide analysis for multiple structures types. Due to this capacity, there are a lot of buttons and design modules that can make this program a little bit intimidating. Similar to other design software, there is always an easier way to modify models to make things easier for the user. So hopefully by showing the versatility of using the wizard input and the MCT shell command, which is kind of a little text input, that we can reduce the modeling time for some of these unique structures, or at very least reduce constant stress injuries required by multiple mouse clicks. Secondly, it's important that the engineers have confidence in their modeling software. So I will provide an analysis comparison between MIDAS Civil and other popular software. In this case, it'll be MDX. And just to show how MIDAS Civil compares, and so everyone feels a little more comfortable with the results that they're seeing from the program. And finally, depending on the job, the analysis, can vary greatly. There are times when hand calculations are appropriate. Other times, simple 2D software can be utilized efficiently. However, when complex geometry is required, 3D modeling becomes increasingly important. This will be emphasized by showing the number of design engineering tricks required to create similar design models using the tools such as MDX. So without further delay, let me continue on with some MIDAS, and let's begin using the program. Okay. So as you see here, I'm all starting with a brand new MIDAS run. And what I'm going to do first is what you'll see is I'm going to activate the wizard module. And this was in the structure. And as you see within this, there are multiple structure types to be used. So there's really a good basis for setting up geometry for a lot of different structure models. For this project, we'll be focusing on steel composite bridge. One thing I also like to mention, and I actually like to do this a trick to myself, is always make sure to be in the right units right here in the bottom right-hand corner. You can change these units to be standardized to every time you open up the project to make sure that they go to the correct units that you're familiar with working with. And right there, as you see, I was working on something recently in metric units. All right, so now in order to make things a little bit simpler and to reduce button clicking, I've already created a input folder for the wizard file, and I'm just going to go ahead and walk through some of these inputs and go through as I discuss them. For the girder type, as previously discussed, we're going to be working with the composite steel eye girder. However, MIDAS also has the ability to lay out geometry for composite steel boxes and composite steel tubs. The modeling type that I'll be selecting is a deck as plate, girder as frame. As you see here, there's multiple design options. The all frame analysis is actually quite popular and something that I like to use in my own design, just simply because it provides the quickest run times. The all plate is very effective when you're trying to get very specific solutions. In this one particular case, I'm selecting the deck as plate and girder as frame, simply because of the way that the straddle bent and the deck interact. They are both rigidly connected to the deck, and so I want to make sure I'm getting that true plate behavior kind of in that tight condensed area between the girders and the straddle bent. This bridge is going to be set on two symmetric 209.5 foot spans with a deck width of 40 feet. The great thing about MIDAS Civil is if you want to have more spans, it's totally possible, or if you want multiple spans, that is also possible. So you could go ahead and have two at 209 and add additional at 310 feet. So there's a lot of flexibility within the modeling wizard. And same thing with support skew conditions. If for some reason you would like to include support skews, this can all be done in the wizard. And then same thing with this layout offset that you see next is working through the wizard, you'll see a number of graphics that really display the best way to go ahead and input all of your model geometry. You see here we'll be working on continuous radius set by, of course, the roadway group at 1,441.74 feet. The curve will be convex, and if for some reason on any of your projects you have a more complicated curve, this can be handled in MIDAS as well. For the bearing type, you have two types. You have bearing type or with substructure. Because the wizard file does not create a straddle pier, I'm not going to select the with substructure feature, but instead what I'm going to do is I'm just going to select the bearing type, and I plan to remove the interior supports created at Pier 1. So I'm going to set Pier 1 as my fixed support, but we're going to go ahead and adjust that later as we begin to modify with the model. And finally, the direction of the support. Please use this for your own particular design needs. Once again, I'll be modifying this later in the file. The next section we get to is the section girder layout and material properties. As you see here, we're working with a deck thickness of 8 inches, and this is standard for the state of Florida. Actually, on most Florida planes, you'll see 8.5 inch deck thickness specified, but an extra ½ inch is an additional sacrificial width and is not part of the structure itself. The haunch height here, I've selected to be 5 inches. For the material, this can be done in a couple of ways. One, you can actually add material. So if for some reason you wanted to add a concrete property, we can go ahead and go through, select a vast library of properties here. And if you select one of those, you'll see the material properties start to appear. And then you can just press OK and it'll show up. In order to save time and not import or add all these at one time, I'm going to go ahead and import the material properties. So I'm going to select this file I already have open, this material properties and other sections. And this is a series of materials I've used throughout this project and other projects. So I'm just going to go ahead and bring them all into this model. So now what you'll see here is that my deck has been specified with a 4.5 KSI concrete. That's standard for the state of Florida. And so please change that as needed for your own particular states or your own particular projects. The girder and the bracing are specified as A709 50 KSI weathering steel. Once again, the use of weathering steel is something that's unique and popular right now in the state of Florida, and that's what the project demands were, so that's why weathering steel is specified. With the number of girders, what you'll see here is I have a 4 girder system set with a beam spacing of 10.5 or 10 feet 3 inches apart. And if we select the guide, it's a good way of layout to see and make sure that you're spacing all of your girders properly for the wizard. Now, for the bracing details, I need to once again insert my now section properties. So I'm just going to go ahead and import a section. And what you'll see here, I'm going to remove a bottom section here. I was goofing around earlier and I duplicated. So what we're going to do is we're going to bring in these section properties. And what you'll see is these are a series of composite girder sections, but also the brace type that we use for this particular project. So now as we do this, you'll see that the angle sections appear under the bracing. I'm going to use a typical bracing system, not a single beam or a diaphragm brace. And the section I took is a V brace, or I like to refer to it as an inverted K, but it's the same methodology. And so as we go ahead here, we're going to change our angle sections. We have our interior brace, and then we are good to go. As you'll see here, I have set this up to have 11 equal spans, or 11 divisions of bracings for each span. This is not something that is necessarily required for MIDAS Civil. There's a lot of information out there. So for example, at the first span, if you wanted to have 10 spans, you could go ahead and have a 10 and 11 designation. So there's a lot of workability available when working with MIDAS Civil. It's just in this case, just due to the symmetric layout, I was able to have the same number of bracing spacings for this structure. Another thing to point out is that MIDAS Civil can also go ahead and use different bracing spacings for each girder. So this is very common for a skewed alignment, for example. And then if there was different support bracing required at the ends or at the piers, this can also be done by selecting this different support bracing tab. When I brought in my girder sections, I don't know if you saw this earlier, but this was actually blank. And the reason why I removed those particular items from the import, which you saw earlier, is so I could have my first section property have a number 1 designation. And so this automatically populated for each one of my girders. This is just kind of a trick that you learn over time, but so you don't have to go ahead and just do a search through a number of large libraries of section properties. Defining the girder section, this could be done by, once again, importing from our previous project, or if you wish to add something, we go to our composite section here, and you'll see that there's a big variety for steel box, eye, tub, composite tees, a lot of options here. So I was using the steel eye section, entering my designated slab thickness, width, haunch height, and then all of the girder properties. I then was also going to use I also used the selected material from the database to go ahead and get the actual composite combination. So once that has been defined, we are now ready to go to the load sections of this analysis. This being a high-level ramp structure that was designed, we had larger barriers, so that's why you're seeing a 1 foot 9 inch wide barrier on both the left and right side of the structure. And the clear distance was set up just a 2-lane, it was a typical kind of ramp configuration. We had a clear distance set up for 36.5, which then equates to 3 design lanes that could be possibly looked at. Before the composite action, for dead loads, what we're looking at here is we're going to look at self-weight, wet concrete. Typical unit weight is concrete, 150 PCF. And as I mentioned earlier, we're having a structural thickness of 8 inches. And then at the barrier, I've doubled up on the barrier to ensure that we're incorporating both sides. And then with the wearing surface, once again, I have 150 PCF and a 1/2 inch. For my moving load analysis, you'll see that MIDAS is capable of having a number of different countries' load conditions and also different states. We're here going to just describe the typical AASHTO LRFD condition. So as you see here, I already have predefined lanes trying to skew as close as I can to the longer side of the bridge. Additional lanes can be added as needed. And then for the vehicles, I'm going ahead and just start the standard vehicles. As you'll see here, I'm going to start off with the HL93 truck, which is a combination of 640 pounds per linear foot loaded, and then also the typical standard axle weights. One important thing, an important catch here on that gets a lot of people kind of confused is a lot of times when we input the dynamic load analysis, we use a factor of 1.33, or people have a tendency to put 0.33. However, with the way MIDAS is set up, you actually define the actual percent. So it's not 0.33%, it's 33%. So, and we'll go ahead and just really quickly add this for the tandem, the truck, and the fatigue. All right, so now that that's been added, we have our typical design trucks in our system, and we are ready to progress. Okay. Now what we've done is we have our vehicle, and we are ready to go ahead and utilize the wizard to create our structure. So as you'll see here, What we're looking at is everything's looking good so far. I'm going to remove the deck just so we can all get a better working of what's happening inside the bridge. A great thing about MIDAS is that it allows you to inactivate specific elements, which allows kind of easy recognition of certain items. So as you see here, we look like we've got our standard K bracing. Everything looks like there's no ridiculous vertical offsets. Everything looks to be placed as actually intended, so that's excellent. I'm going to work here from the top, and just to show you that at this location where my mouse is scrolling around right now, this is going to be the element that we're going to remove to create our straddle bend. And now the removing of this can be done in numerous ways. We can use the selection tools, select, and we can use our window, and we can start selecting items. Now I'm not a big fan of using this exact method just because of what you see here. It's pretty easy to accidentally click something that causes us to accidentally delete a member that we never intended to delete. So what I'm going to do is I've actually gone ahead and documented the actual elements that need to get removed, and we're going to remove them right now. So I'm going to select the nodes that I would like to get removed. Sorry for the typing noise. Okay, and then I'm going to go to my element. I'm going to go to the delete element. And so I have my selection. We're not dealing with free nodes here, so we want to make sure we deselect that. And let's make sure we're here. So right here, these ones that are shaded purple are the one we're going to move, and let's do that. All right, so as you see here now, I've removed all the members and the elements for that one particular bracing line. And so now what we're ready to do is add the nodes for the straddle pair. In order to do this, this can be done, once again, a number of ways. We can use our tree menu and our tables, and we can go ahead and use the XYZ coordinates for which we plan to use apply our nodes. But the thing that I like to do, and I mentioned this previously, is the use of the MCT shell command. So if I go to Tools and I select this MCT command shell, this gives me ability to do insert command for nodes. And so what I've done is I've already pre-calculated all my node locations using just interpolation and extrapolation of the required girder line. And as you see here now, I have all of my required nodes set upon this line. We'll save this model in just 1 second. All right. Now, in order to apply the members, this can be done either graphically in tables or once again through the shell command. So if I wanted to, I could go ahead and take my element and I could create elements. Oh, actually, one thing that I forgot to do is we still have more members or more inputs to do. So we're going to change this. We're going to add some more section properties. Oops, I'm going to import some more section properties. All right. And what I'm going to do is I'm going to remove everything from, I don't need any of this information. So we're going to get rid of this. And we're going to import this section properties. Okay. So now what we've seen here is that we have the proper and all of our section properties in the model. And now what we can do is go ahead and either do it, like I said previous, graphically, or I can take my my weathering steel. And as you see on this particular instance, when we designed this, we actually needed 70 KSI high performance steel. And you'll also see a 1.1 factor. And that 1.1 factor was we had additional 10% of self-weight to this to account for the additional detailing factor required for the straddle bend. So we're going to select that material property, and you can go ahead and go piece by piece and click to draw all of these members. You could also do the same thing using the table, similar to the elements or the nodes previously shown. And we can go ahead and we can select a beam member and also fill out all of our properties. In order to make things just a little more simple, what I'm going to recommend that we do is once again rely on the shell command. So I've already predetermined using those same members as using the same designation. I've created a group of text chains to do the shell command. And I'm going to use the element, insert. And so as you see here now, I have all of my straddle pier ready to go. And as you go ahead and if we can highlight these, what you'll see is that each one of the straddle piers has a varying section dimension as you go along. And this is also shown in the element section. As you look here, we all have the same material. It's that high performance weathering steel, but we have properties 1, 2, and 3. So just very quickly, we are able to quickly switch and apply different property sections between all of those unique areas of the straddle pier. Using similar methods, just to kind of quickly advance here, using the shell command, what I'm going to do is I'm going to then apply my columns. Once again, this is just quick and easy, and most of us as engineers, we also like to have our own specific spreadsheets that do our own calculations. So as we look down here, we've seen that we created nodes on the left and the right column. Now I'm going to switch over to the element. I'm going to bring in my column sections. All right, I'm looking for the word element. Apologize for the lack of reading. All right, and so now we're going to bring in these column members using the shell command. And now, as you see here, we have a fully formed column section. One quick item to note, as you see here, we are not, when I brought these in, I did not specify an angle. So they were brought at the 0 perpendicular to the global coordinates. So if we quickly go to our elements for these last sections here that I just defined, and we change, sorry. Okay, that's going to create a little side node there that I need to delete. I apologize. So we're going to go ahead and revise these angles between our new column section. And so now, as you see, by just doing that quick adjustment, my column and my rigid link there are shown in the exact same plane as my straddle pier. All right. So now that we've done that, the only last thing to do is define our boundary conditions. It's important for a situation like this, for our structure here, we created this and we supported it on disc bearings. And so they're very, very rigid. So because of that lack of compressibility, I'm not going to model them as elastomeric bearing pads or elastic links. So I'm just going to use the rigid link command. And so I'm going to connect these two members on both sides with rigid links. And the way this can be done is we open up our boundary section and we select rigid link. And we can just go ahead and I recalled all these nodes by memory. But we're going to go ahead and we're going to make this left side a fully pinned condition. And we're going to make the right side a slider condition. So what you'll see here is I'm not going to select the Y direction. So as you see now, I have a rigid link. Sorry for the faintness of the font. I was goofing around with stuff earlier. And so I decreased it a little bit. So as you see here now, I've got two rigid links, and you see the series of 1 and 0s, and those relate to the rigidity that I'm requiring for this rigid links. The last thing I need to do just to make sure that we have these in the proper orientation is I need to go ahead and I need to revise my node local axis. And so by doing this, right now, I currently have those rigid links set up within the global coordinates. But however, we all know that this is going to move transversely to itself and not to the universal Y direction. So because of that, what I need to make sure is I rotate the orientation of this two axes to make sure that these releases act in the proper direction. So if you see here, I've got my Z node local axis now pointing vertically. Let me do this from the top. My X vertical axis going longitudinally, and my Y going transversely. So the fact that in the last rigid link, we went ahead and removed the Y direction makes sense. And now the reason why we did this is because if you have two pinned conditions under the under thermal loading or any locked-in stresses, when you're pinned, you can create a lot of forces on your column. And so this is what we're trying to avoid by releasing the straddle pier transversely at the lower side there. Finally, we're going to go ahead and add some final supports at the bottom of each column. Because this structure is supported by a large pile bent footing or a pile slab footing, it's pretty common under these instances for engineers to model this as a fixed footing. It's slightly conservative in most cases for most design instances. However, MIDAS does have the ability to provide springs as needed. For example, if you have a drilled shaft footing or a somewhat flexible footing, or you're really trying to get exact analysis to reduce column forces. So we've gone ahead and we've now provided supports. You can see them, they're in this green shade right here at the bottom. And so now both columns here are fully fixed. And finally, what we're going to do is we're going to go ahead and delete the members that the MIDAS wizard created. And we'll do this real quick, just visually show you. We'll go display, and we're going to go to the boundary conditions, and we're going to show the supports. So when I initially did my initial MIDAS wizard, what you'll see here is we set pier 1 is fixed, which is why you're seeing these supports appear at this girder line. And so what we're trying to do is making sure that we do not account, we remove these from the analysis. So we're going to go ahead and do just that right now. And they are sections 47, 140, 233, and 326. And that's just the case for this structure. Not all pier 1s are those numbers. As we sit here now, our supports are gone, and we now only have supports at the ends of these structures and at the bottom of each column. And you see here, we're dealing mostly with a pin conditions, or not pin, sorry, just a vertical reaction with only a little transverse resistance. And so that all makes sense to me. So I think that we're good to go with the analysis. When working with construction stage analysis and live load analysis, especially for a plate, the deck model as a plate, this process can take a little bit of time. So in order to do that, what I'm going to do is I've actually already ran a model, and I'm going to open that up right now. And so while that's opening up, we'll go ahead and we will discuss the live load. And so as I previously stated, there's kind of two ways to look at this deck. They either do a frame model or a plate model. What MIDAS does is applies traffic surface lanes when plate models or plate elements are used to create an influence surface, and it's going to use this influence surface to then place vehicles. When you're using a frame analysis, the traffic lane lines is used, and this is done to create an influence line, which is then used to place the vehicles. One thing that's a little bit interesting about MIDAS is that it does have the ability to place dual trucks for all of your analysis. But when placing those dual trucks, you need to select where the start of each span for continuous structures is. So we'll get into that in one, I'll show you exactly what I'm talking about right now. So now as we're dealing with our structure that has already been analyzed, I'm going to go ahead and I'm going to go to my loads. And this is where you apply any additional dead load, moving loads, or construction state loads is in this tab. I'm going to go to my moving loads, and I'm going to go to my, I believe it's traffic surface lane, and I'm going to select my left lane here. Okay. So what you'll see here is this click for span start. So this is obviously my first most point right here. And so that's obviously going to be selected automatically by MIDAS Civil. But as we scroll down, what we have to be aware of is that there's this extra node around 1451. Oh, sorry, 1440, which is then also going to be the location of the second span starting. And so if I were not to click the second span and run my analysis, MIDAS Civil would not automatically place that truck around my second support. So it's just something to be very, very cognizant of when you're using this if you're not seeing the live load results that you were looking for. And so now we're just going to look real quickly to make sure that MIDAS seems to be placing the trucks correctly. For that, I'm going to go to my results, and I'm going to look at my moving load tracer, which is right here. I'm going to look at a reaction point. I'm going to look at my left reaction, which is location 10,005. And I want to look at one truck, max vertical load, FZ, at this node. And we'll just go ahead and apply this. And so what you're seeing here makes perfect sense to me. We're seeing the effects of a lane load, and we are seeing two trucks centered about the straddle pier. So it seems to me that the program is working as correctly, at least in this negative moment region and for this max internal reaction region. One thing to point out is that for the standard truck, they have two 32 kip axles and one 8 kip axle. As you see here, we've got 14.4 and not 16, so that's a little bit interesting. But the important thing to know is that we use the 0.9 reduction factor per the AASHTO code when you have this two truck condition. So 16 times 0.9 is 14.4. And so all these numbers actually make sense. And they're kind of tough to see, but if you zoom in here, you will actually see this is 3.6, and that is 4 kips times 0.9. So MIDAS is taking into the reduction of the two truck condition. And then just really quickly, I have multiple conditions here set up, but let's just see if 2 lanes, we should be seeing another truck right next to it, and we do. Oh, apply. So what you see here is a truck almost identically placed right next to it, and if we were to do a 3 truck condition, we would also see something very similar. So that is all making sense to me. So right now I feel very comfortable with the negative moment region. As I go to the beam forces, I'm going to look at a simple span structure, or a positive moment within this first span. I'm going to look at the MY, and I believe a good node to select would be 475. And we're going to look at 1 truck to the left. So as you see here, I selected a node or a member that's right in the middle of this first span, and you're seeing 16 kips. You're seeing 1 truck condition here, not 2 trucks, so that makes sense. And you're seeing the 16 kip axles, and that right there is saying that the 0.9 reduction factor is not being applied. So this is all making sense, and I feel comfortable with what MIDAS is doing for the live load for both the positive and the negative moment regions. So that just right there hopefully gives everyone just a little confidence on how this program works. And also, here's just a visualization to use when you're looking at your own results. As we go down here, now that we've verified live load, let's talk about construction and construction stage analysis. As an engineer in Florida, I'm going to use my local DOT criteria as an example. However, DOTs across the country are increasing their expectations with regards to erection sequence analysis and plans development. Here in Florida, the FDOT has the following criteria for all steel girder bridges. And the things to highlight is that we have to evaluate for stability for construction use under wind loads, and also temporary construction loads per other criteria of the SDG, which is the Florida Structures Design Guidelines. But the other interesting thing about what the state of Florida requires, and I've seen in other states, is that for all steel girders and for bridges on false work, include in the plans a workable erection scheme that addresses all major phases of erection, investigate superstructure stability at all major phases of construction, consistent with the erection scheme shown in the plans, show the required temporary support locations and associated loads assumed in design. So what we need to do now is create a construction stage that allows us to get our temporary support loads during our erection sequence. And so just really quickly, just want to show you in MIDAS, and I'll explain these inputs in just a second, just kind of the construction stages that we're seeing. The first stage here, and let me make it pre-rendering. What you'll see is the erection of just the column and the straddle pier. And then as we go to the next results, you'll see the erection of the first girder pieces attached to the straddle pier. And for simplicity, what I'm going to do is I'm going to show my supports. So as you'll see here, I've provided false work and temporary supports at each of those locations to make sure that the girder is stable. Now we're going to go ahead and finish off the second span for the exterior, the innermost girders, and we're just going to slowly work our way through the girder doing our erection sequence. During all of these systems, MIDAS is logging the reactions for each of these, and we'll go through and show that in just a moment. As you see here, we're now going to remove those interior towers, which is being shown, and we are going to finish off the erection of the first span. And then finally, we have our step final where we're going to remove this last internal reaction, and we are going to then pour the deck in one complete segment. Now we're going to talk more about the importance of applying the proper way to apply deck later, but I just wanted to show you how this is done and how it can be done in MIDAS Civil. So if we go back to our final step here, also one thing to show is that in each one of these, I'm applying wind load as well to this entire structure, and this occurs in multiple stages. It varies, the limits vary stage to stage. So there's also wind load and dead load applied to this analysis model. And now, if you were want to duplicate a similar kind of construction stage analysis, what we do is we're going to go to the load condition and we're going to select the construction stage. We're going to go to define construction stage, and you'll see here that I have a series of stages set up in order to complete this analysis. The first being straddle erection and then the erection of the girders. When we go here, we'll go show us steps. The important thing to know about when working with MIDAS Civil and the construction stage analysis is that the creating design groups is very, very important. Everything is worked off of group lists and not element and numbers, individual element and numbers. So you need to be careful when you're creating all of your inputs before you start the construction stage analysis that you feel you have acceptable amounts of groups set up. So as you see here in this first section, I'm activating the groups of tall column, short column, which is the left and right due to super elevation. My first little bits of girder segment, which were the first segments that are bolted onto for the first erection, and then the straddle pier. And then activating boundaries. And at this time, I'm not applying wind, although it can be easily. I'm applying self-weight. And just to show a quick example here, on the next stage, what you'll see is that I'm now activating more elements. I'm activating more boundary conditions to show those temporary false work conditions or those temporary support conditions, and also to change the rigidity of the straddle pier. On the first step, the contractor is going to have to go ahead and apply blocking to the straddle pier in order to make sure that it remains stable. Once that first step is done and these first girders have been erected, then what we can do is release those blocks and change the locations there at the straddle pier. So what you'll see is a series of sections. And as I go to the towers removed, the thing I wanted to show you is that it's also possible to deactivate conditions. So in this particular case, I am actually removing some of the temporary towers that are used to support the structure. And that can be seen once again as we work our way just visually. Here's it with the towers removed. Here's the section with the towers. So between there, I am deactivating those conditions, and that is creating our construction stage. So I'm going to go to my final girder erection, and I'm going to go to my results. And because, as I previously stated, in Florida, we have to tabulate all of our reactions due to wind and dead load during construction. MIDAS makes this process very simple by selecting certain stages. We can go ahead and select all of my stages through analysis. And as you'll see here, for each node, it's going to go ahead and give me the respective results for each node and each construction stage. Another important thing when working with MIDAS Civil is it gives you the ability to sort. So if you wanted to focus everything on the actual construction stage, I just go to my sorting dialog, bring over the stage, and I raise up the priority. And that's going to support all my results now. So all the results from stage 1 are shown. As you see here at this location, the only supporting the straddle bent are just the columns, so that makes perfect sense. And as we move our way down the stages, you'll see more and more boundary conditions be activated with different results. And so what this does is it provides us a really easy way to go ahead and get our wind and dead loads. You'll see here that I've called my wind load erection load 1, but if you go to the analysis construction stage, that name is not, that is my own preference use for a name and nothing set by MIDAS itself. So there I'm selecting the wind load case and all my inactive load cases. And when I said inactive load cases there, this is something that's for Florida, where there's a construction active wind case and a construction inactive wind case. During the inactive phase, the wind speeds are a little bit higher because no workers are present at the site. So once we have that, we've successfully investigated the construction stage analysis, or the girder erection analysis, and we can move on to the construction stage analysis. The deck pour sequencing, and just really want to stress here the importance of deck pour sequencing when working with composite structures. Just read these little excerpts here. Composite action is obtained between the girder and previously poured slab sections. This affects the moment of inertia in the previously poured sections and greatly increases the stiffness of the section. The distributed forces, or the distribution of the forces affected by the previously poured composite sections. The eventual accumulated moments, shears, and deflections at a given point are different from a stage analysis than from analysis assuming simultaneous placement of the deck. So as we previously just discussed, in my last model, I showed the deck being poured in one continuous sequence, and that is incorrect. So real quick, I'm going to go open up another MIDAS model that shows how this is done in order to properly do this. Sorry, this should take about 13 seconds, 30 seconds. And so all this is opening up. The thing that this will really kind of show itself is in the deflection analysis of these structures, which we'll discuss in just a little bit here as we compare the results between MIDAS and MDX. So what you'll see is the exact same structure as we previously looked at in both cases, except we have a slightly different construction sequence during the first step. And let me once again make it a little prettier. Never mind the purple girder, that was just me trying to make things pretty for a graphic. So in the first step, what you'll see here is just the girders erected and without any deck poured. And what it'll look like in this particular next phase is that nothing has been applied to the model, but that is not necessarily true. During this step, what we have done and what MIDAS does is it applies a wet concrete load to that erection, or to that first deck pour region. So what you'll see here is there's no composite action yet, just dead load on the structure. As we move to our next deck pour, what you'll see is we now have a composite section on the first section and now wet concrete on the second span. I'm sure everyone knows this, but it's very important to pour your positive slab moment regions first. But any young engineers, do not do your first concrete pour and then ENG moment region. And so once again, we go ahead and we look at this and we move down the process. What you'll see is now we have the positive moment regions being composite, as shown by the deck section, and now we just have wet concrete load applied to the structure in the middle. And then finally, we reach a segment where we now have a fully composite deck along the length of the structure. And at this location, once again, moving loads and final design loads can be applied to the structure. So once we've gone through this entire process, what you'll see is now we've accounted for the importance of the deck pour sequence. Minimize this quick. So now that we've done this, I want to get into the discussion between MIDAS versus MDX. The nice thing about MDX, it allows the analysis of unique substructures. It has a flexible process to allow multiple 3D analysis software, or the flexibleness of 3D analysis software allows users to account for all this kind of complex geometry that we see when you incorporate straddle piers. And also, traditional analysis requires a separate analysis to accommodate all these geometric constraints. So if I wanted to use this similar process for a program like MDX, what I have to do is I have to use my MIDAS model and apply forces to it to account for spring conditions. So by doing this, what I did is I placed a 1,000 kip load above each girder line. I then took my load, my deflections created by these 1,000 kip loads, and used the force divided by the deflection to create a spring constant. There's no particular rhyme or reason why I used 1,000 kips, except for when I used one kip, the deflections were very small, and so it made dividing a little bit of a pain. So that's the reason why I decided to go with a 1,000 kip load. And so just to show you how these two programs line up, there's a lot of great similarities now that we've used MIDAS to create the appropriate springs that MDX can actually use for its analysis for these kind of structures. As you see here for the dead load for both shear and flexure, first we'll talk about shear, we see almost identical moments within the positive moment region. As we move to the negative moment region, we're noticing that MIDAS Civil is collecting a little bit more negative moment over the straddle pier, and then they're once again aligning very well in the positive moment region. And in interior girder, we're actually seeing the exact opposite behavior, where the MIDAS is seeing a little bit less negative moment than MDX. And this is due mainly to the load sharing, the 3D load sharing capabilities that MIDAS is capable of, as opposed to just applying vertical springs to the model. For the shears, what you'll see here is that we have, once again, very, very good coordination between the two models. So which is very, very good in terms of giving everyone the confidence that MIDAS Civil is capable of handling just this kind of analysis. Just don't worry about the slight offset created between these two lines. This was created just simply because I grabbed the J node during all of my analysis. If I had selected the I node at this point, we'd have a true vertical line here as well. But once again, the interior girders and exterior girders are showing very similar dead load shear results. Live load shear, we're seeing almost the exact same behavior. The exterior girder is seeing a little bit more negative moment than the interior girders. And all in all, the programs are lining up very, very well. As we incorporated this, we definitely saw less than 5% differences between the two models. And once again, comparison for the shear, the live load shear, once again, a lot of similarities between MDX and MIDAS. So what we're seeing here is a lot of good positive results here that the MIDAS springs in the 3D analysis are working correctly. Going back to the importance of the construction sequence and the deck pouring sequence is that first, these deflection results, they look a little bit not what you would expect because they're not symmetrical while the structure is completely symmetrical. And this is entirely due to the deck pouring sequence. As you see, we poured the deck pouring sequence first on the first span in the previous model. So what this is causing larger deflections during when that first wet concrete is applied. And then as the section goes composite, we're seeing less deflection effects in the second pouring sequence. So this right here is the exact reason why it's important to have a good understanding of deck pouring sequence. Because if we were to look at our results when it was just a single deck pour, what you would see is a perfectly symmetric W shape here. And so therefore, we could be analyzing the wrong camber information, and we might have to make costly profile adjustments in the future. So always be careful about considering deck pour results during this. As we go through and scroll on, you'll see that more or less, we're seeing the exact same results between the interior and exterior girders. One thing that's very, very nice, because we also have to provide camber information for the straddle pair, is we're seeing at the actual girder locations, we're getting very, very good comparisons between our calculated springs and MIDAS's 3D analysis software. So what we're seeing here is that this gives us a lot of confidence that the camber information provided for the straddle bent will also be accurate and reflect the final conditions out there in the field. And so with the end of that, I have finished my discussion and presentation, and I'm going to go to some questions.
Yes.
Apologize.
Yeah, please go to the questions tab and expand the tab, and you'll be able to. Yeah, you could undock the pane from control panel on the right.
Okay.
And, or I could, you know what? I could bring it up for you.
Okay, let's go ahead and do that.
Okay, I'll do that.
Okay.
I'll scroll this up. Yeah. So here are some of the questions that. Do you see the questions?
1 second.
I'm not sure. Okay.
Oh, do I need to make you?
Okay. Okay. Should I just read some of them out to you?
Yes. Let's go ahead and do that.
Okay. So the first question is, the model method is girder using beam element and deck using plate element. Then the composite beam element is used. I wonder if the deck stiffness is counted twice in the model, once in the composite beam element, then in the plate element. Yeah, that's the question.
Yeah, well, I mean, so the first thing to realize is that when you go ahead and you model the composite section, that's more of an design tool than it is an analysis tool. The reason I have full confidence that this model does not go ahead and account for the double stiffness of the deck is because the only thing that the comparisons between MDX and MIDAS is that we showed almost perfect deflections. And if we were to add an additional double dipping of the stiffnesses between those two, we would not have such good similarities between the two analysis software in between the support conditions. Obviously, where we use the springs, we'd have very similar results, but in between there, we wouldn't see such a good alignment. So there is not a double dipping of the deck sequence there, or the deck stiffness.
Okay, I'll go to the other question. So is the structural wizard capable of modeling splayed truncated girders on a curved steel structure? Truncated girders on a curved steel structure using the wizard.
Now, the way that I believe the best way, and this is actually more of, there's a lot of good MIDAS software analysis and programs around, but when using the wizard, what you are capable of doing is provide multiple girder sections and arrangements along the structure. So as you define more girder sections, and what you can do is then modify the girder sections along the length of the girder to account for that that splay, which I believe is, I think we consider like a dabbed kind of structure or a tapered section. So if you're trying to create a tapered section, yes, that is possible in MIDAS Civil using the wizard. And there's actually a couple of great tutorials on YouTube for how to do that.
Okay, so the next question, did your support springs for MDX change between dead load and live load analysis? And did they also change per deck placement sequence due to changing composite properties?
Yes. What we actually noticed is that we looked at three conditions. We looked at a dead load only spring condition, we looked at a live load only spring condition, and we looked at a 1000 kip vertical load spring condition. And we were noticing that, yes, they did change, but it was very, very small changes. So something would go from 250 kip per inch spring condition to 235 kip per inch spring condition between dead load, live load, and the point load applied. So yes, there was small similarities done between all that. However, they were not noticeable enough to cause a large differential in analysis. So what we actually did was applied the average spring effect between all of these conditions, and we were very happy with the results. And then with regards to the deck sequence, yeah, I highly believe it's very important to always model the correct the correct deck pouring sequence. There's just a buildup of forces and moments created regardless of what happens with the deck pour, or as a deck pouring sequence occurs, there's a buildup of shears and moments, and this is discussed a lot in the NSBA handbooks. So because of that, all of those effects, all those different loads, all those locked-in forces, all the changes of behaviors will create different springs. So make sure that you always apply a deck pouring sequence when using a program like MIDAS Civil.
Okay, so let's go to the last question.
Okay.
So did you modify the stiffness of rigid link between column and straddle bent to match stiffness of bearing pad?
Okay. In this particular instance, I did not. There is certainly merit to be doing that. It all depends, I believe, on the type of bearing that you have. When you go ahead and you have an elastomeric bearing pad, I believe that there's a lot of merit in accounting for that change in vertical stiffness, and MIDAS Civil definitely can handle that process. However, because in this case we're using the disc bearings or pot bearings where the vertical displacement isn't very prevalent, especially under just pure compression loading, we did not go ahead and model the vertical stiffness of those two connections. However, it can be done in MIDAS, and it is something that does have merit if you're not liking the results that you're seeing. In fact, that was actually something that we kicked back and forth, but as we started to play with the numbers, we weren't getting the stiffnesses we were getting for our particular bearing pad were quite large, so we decided to omit it.
Okay, thank you very much, Nathan. I know there are other questions that weren't answered, but if you want those questions to be answered, please reach us, MIDAS, directly. And thank you very much for your presentation. And this will be the end. And I hope everybody enjoys the rest of the evening. Thank you.